Welcome to part 3 of advanced forecasting. We have to just cover one more forecasting technique, which is very popular, widely used, and so it's extremely important that you continue to pay attention. And we are very nearing the end. This is perhaps going to be even more intuitive than the ETS technique you've learned about. Okay, so these are called ARIMA models. You'll soon learn why they're called ARIMA. But before we can get to them, these models, when you use these models, it'll often come up a discussion of stationarity because the core model applies to the stationary time series. These models can handle non-stationary time series, but they do some transformations, then apply the core model, and then they undo those transformations to come back to the original scale of the data. So don't worry, that doesn't mean you're limited to only stationary time series, but because if you are going to use these models and you use software packages that apply ARIMA models, you're going to come across this term stationarity. So you need to have some idea about what it is, right? We're not going to get into the mathematical requirements and proving stationarity or doing tests for it, but the basic idea you need to know. A stationary time series is one whose statistical properties do not depend on the time at which you observe them. What it means is that the key statistical properties like the mean and variance don't change over time. Now that immediately excludes trend and seasonality, because trend means your mean is increasing over time. Seasonality means your mean level is changing across the seasons in a year. So if you have trend or seasonality, you're not stationary. So how can we even use this method when a lot of the time series we deal with are going to have trend, are going to have seasonality? Seasonality is extremely common in sales data, and often for business supply chain operations planning, we are forecasting demand based on sales data. But again, as I said, don't worry. If the time series is non-stationary, the method will handle it, but you still need to understand what is stationarity. Okay, so ARIMA analysis. Well, maybe I should take out the I. ARMA analysis, because the I part handles the trend. So if you just think of the precursor to ARIMA, AR models, just the first part of that, or MA models, or combined ARMA, ARMA models, the precursors to ARIMA. They require a stationary time series. So let me fix that. Okay. Now, if your time series is not stationary, transformations are done to stabilize the mean and variance before the model is fit. And then after running the model, when they do the forecasting, they can undo those transformations and you still get a proper forecast. So we really don't have to worry about it too much. So let's look at 9 examples and see which ones are stationary. So stationary means, for most practical purposes, the mean and variance are not going to change over time. So the green tick marks are stationary time series. Okay. Google stock price is, even though there's an outline does not mean the time series is not stationary. Even though there's a couple of outliers here, majority of the time series, the mean is around 0. Because it's the change in price. Sometimes the change is positive, like plus 5%. Sometimes the change is negative, like minus 3%, right? And so the mean is 0. And if you look at whether you measure the mean between January and April 2015, whether you measure the mean in this time period, you get a mean of 0. And whether I measure the mean here, I get a mean of 0, right? So mean is stable. It doesn't depend which year you calculate the mean over. The change in the Google, not the Google stock price, the stock price might be going up, but the change in the Google stock price is stationary. Okay, let's look at, this we'll talk about in the end because there's these cycles here, but it's a little bit more complex. Let's talk about Google stock price, not the change, the actual closing price. If I look at the mean around 2015 April, the mean is around $550. Okay, and if I look at the mean around October of the same year, the mean is somewhere here, which is about $625. So the mean over a few months has changed by $75. The mean is dependent on time, and you can see the big jump here. So the mean is clearly changing. You can see, it's hovering here at this part, it's hovering here, then it's going up here. So the mean is jumping up, and so it's not stationary. Okay, there's a trend or large changes in level, which is making it not stationary. Same thing with egg prices in the US. Egg used to be very expensive, 1900s and 1975 they become cheaper. You can see this trend. So that's not stationary either because there's a trend. Okay, pigs, consumed for meat in Victoria, Australia. Okay, again, you can see a trend going up for this part of the time series, then a trend going down for this part, and again going up for this part. And different times, the mean is here, then the mean is up here, then the mean is down here. So the mean is changing over time. So again, trend or large change in level, not stationary. Same for strikes, number of strikes in the US, like any union going on a strike. And so you can see that it's averaging here and then averaging about here for this time period, averaging up there for that time period. So there's a trend and then a downwards trend, and also large change in level from here to here. There's a big jump. So that's again not stationary. Okay, let's look at seasonality example. So beer production in Australia right here. This is quarterly data, so you can see seasonality. You're not going to see seasonality in annual data. This is annual data. You're not going to see seasonality in annual data. Remember that, because seasonality is a pattern that has a cycle or a time period of a year or less. You could have 12 months data and you can have monthly seasonality. You could have quarterly data. You could have seasonality over 4 quarters in a year. You can have daily data. You could have seasonality over a week, like Sunday to Monday, and so on. You can have hourly data. You can have seasonality on the working hours or things like that, like electricity consumption. But you're not going to have seasonality in annual data, because seasonality by definition is a pattern which repeats every year or a fraction of a year. And so annual data has no seasonality. So let's look at quarterly data. You can see that this is quarter 1. So this is quarter 4. So every quarter 4, you get a big peak. Every year in quarter 4 is a big peak, holiday season perhaps. A lot of people consume beer in Australia at that time, I'm guessing. And so you see clear seasonality. So if I was looking at the first 3 quarters of the year, the mean would be down here. But if you're looking at the 4th quarter, the average consumption goes up there. And so, the mean changes based on the season. So it's not stationary. House sales, again, there's seasonality. This is monthly data. And you can see that in the summer months, there tend to be peaks. Even when, most years, if you look at the summer months, there are these peaks. So there's seasonality there. So again, seasonality means if you look at the summer months, you get a very high average. You look at the winter months around January, you get a low average. So the average depends on winter versus summer. So that's not seasonal. Let's look at another example of trend with seasonality. So this is quarterly data on gas production. Again, the seasonality, because winter people use more gas to heat homes. And as the trend increases, the level of the time series, the fluctuations increase. The seasonal fluctuations are much larger here, like about this big, versus down here, the seasonal fluctuations are small. So the fluctuations are increasing as the level of the time series is increasing. So it's not stationary, but also think about how you're going to model the seasonality. You're probably going to choose a multiplicative seasonality model, because as the level goes up, seasonality goes up. So if it's like plus minus 30%, as the level goes up, the amount of 30% of the level is a bigger amount of which it goes up and down by. Okay, so we already talked about why the change in Google price is stationary, because we saw that the mean is about this. You might say about here the mean is a little bit higher because of the outlier, but you want to exclude the outlier and look at the non-outlier part, because when you're forecasting, sometimes you have to handle outliers specially, or remove them, or really think about what happened here, and can that repeat, and so on. So don't worry about outliers when trying to think about stationarity. Now, why is links trapped in Canada? This is stationary. First of all, it's annual data, so there's no seasonality. So what's these peaks we see? These are what we call cycles. So the population has cycles. The population goes up, comes down, goes up, comes down, but these cycles don't have the same time period. So here they may last 5 years, here they may last 3 years, here they may last 7 years. So the time period for a cycle is kind of random, okay? Unlike seasonality. Seasonality has the same cycle. It repeats after every m time periods always. So this has a different time period. So what happens if you take time windows? So let's say I take a 10-year time window, I may get a mean like this. Now, if I take a 10-year time window here, it's just 20 years, 20-year time window. If I take a 20-year time window here, I get a similar average. Why? Because the width of the cycles varies. I end up getting equal number of peaks and troughs. If I pick a really small window, the mean is gonna change over time, right? But if you pick a longer window, the mean is not changing over time. So the question becomes then, why are we saying this is stationary when we said here in seasonality that this is not stationary? We said this is not stationary because the mean changes over the seasons. Here, if I took a long-term approach, I took an average of over an entire year, I may get a mean something like this, and the next year I may get a mean of the same level. The reason being because it's quarterly data, you're going to forecast for the next 4 quarters, and so the seasonality matters. So you need to look at a smaller time window because you are working at a quarterly time scale. You have to forecast quarterly. For cycles, usually when you have so much data and you are going to incorporate the cycles in your forecasting, you're looking to forecast 5-10 years out. Okay, so that is why for 5-10 years out, the average level for the next 10 years might end up being the same as the average in the past, because you'll end up having 3 cycles or 2 cycles over the next 10 years. But if you were to forecast just for next year, then the cycles may become a problem. So it kind of depends on your forecasting horizon here. In general, because the cycles are unpredictable, that unpredictability of the cycles, and that sometimes they last a long time, sometimes the cycle is very short, that's what causes us to say, okay, this can be treated as a stationary time series, and usually we're forecasting over the long term, so we will get a bunch of cycles in that long term. For seasonality, we're usually forecasting over the short term for the next year, and so you have to factor in the seasonality, as we can't assume stationarity. Okay. Anyway, if it doesn't make sense, all you need to know is this: if you have a trend or seasonality, it's not stationary. If you don't have trend or seasonality, basically for our purposes, it's stationary. Okay. And what does stationarity mean? Stationarity means that the mean and variance are stable over time. Non-stationary means the mean or variance or both are not stable over time. So that's the conclusion you need to know. Okay. Now, I talked about how we can do some transformations to make a non-stationary time series into stationary. So these are 3 popular transformations that you should just be aware of. The first one is called differencing, where you take a value of the time series and you subtract the previous value. This is how we this is what happened when we went from Google stock price to the change in Google stock price, because any value minus the previous value gives you the change. So you can notice that the original time series of Google stock price was not stationary, but when we took the differentiation, we differentiated the stock price by taking each value, subtracting the previous value, the change in the stock price becomes stationary. So that's a very important transformation. We can just do differencing, and that basically removes the trend. Okay. You can do another, if the trend is still there after, because if you have a non-linear trend, first time you difference the time series, you still get some trend left over. So you may have to differentiate it twice. That's called a second order differencing, where you take the difference time series, the y comma, this one, and you difference this time series you got from the first time, and that's called a second order differencing. Okay. Now you can also do seasonal differencing, which is just like differencing, but from each value of the time series, you don't subtract the previous value. Excuse me. You subtract the value which is the previous similar time period. So if your monthly data from January, you subtract the sales and the previous year's January, not the last month of December. In differencing, you would subtract from January the last month December sales. But in seasonal differencing, from January, you'll subtract last January. From February, you'll subtract last February. From August of year, whatever year you're in, you'll subtract August of the last year. And from August of the last year, you subtract August of the year before that, and so on. So that takes care of seasonality, because whatever seasonal boost you get in August, that gets subtracted out. Whatever seasonal boost or a trough you get in January, that gets removed when you difference the Januaries, right? So you subtract from each time period. You go back M time periods. M again is the number of periods in a seasonal cycle. So for monthly data, that's 12. So you go back 12 months. For quarterly data, M will be 4. So you go back 4 quarters. So from quarter 1 this year, you subtract quarter 1 last year. So that's differencing with a jump, where M is the number of seasons in a year. Log transformation can often stabilize the variance if you have a time series that's growing and its variation is also growing, like the one I showed you here, gas production in Australia. Then you can take a log transformation, and that will often fix that problem. Now, usually, software will handle this automatically. It will transform it so that it's stationary, so you don't have to worry about it. But sometimes it may give you options, or the output might say we use these transformations. So it's useful to know the basic, differencing, seasonal differencing, log transformation, the basic transformations. Okay. Now let me show you an example. So this is anti-diabetic drug sales. You can see that there's seasonality because the sales peak around the same. This is monthly data. So every year around the same month, the sales peak. So there's seasonality. So in addition to seasonality, we also have increasing variance. Look at the jump, the peak versus trough for this year on the right hand side. The variation in this year is a lot more than the variation in the past years. So the variation is also growing. So first we're going to stabilize the variance being a log transformation. So that's the second plot. So when you take the log transformation, log of this value, you can see that the variance has been stabilized. So there's no more increase. There's increasing trend, right? But there's no increasing variability. So we did a log transformation and it worked. Then we take a seasonal differencing. Okay, this one, YT minus M, it's monthly data. So from each value of the time series, we'll go back 12 months. So we'll subtract YT minus 12. So the same month last year, that will be subtracted. Now, when we do this seasonal differencing, this is what we are left with. And this seems to be stationary because the mean is stable, right? And the variance is also stable. Okay. Now, what about trend? Like we saw a trend and we never did differencing. Well, if the trend is not very not very extreme. It's like a slow trend, like a small slope. Seasonal differencing will sometimes be enough to remove seasonality and the trend, because the growth over a year is very small. So if you look at this, so this year versus the next year, the mean is about the same. There's not much growth. So when you subtract the previous year from this year, you remove the seasonality and you remove the little bit of growth that is there over the year. You're not growing that much year upon year. So the seasonal differencing gives you that. So these are the two transformations we'll use. We'll do a log followed by seasonal differencing, and now we have a stationary time series. Now we can run our models, okay? And then afterwards we can go back, we can add back the seasonality, and then we can take the inverse log transformation to go back to the original scale. And the forecast will be on the original scale. We'll undo the transformations and we'll get a forecast on the original scale. So you don't have to worry about doing it manually. The software will take care of it for you. Now, you can also do a unit root test to see if the time series is stationary or not. A popular test is called KPSS. Okay, the null hypothesis is that time series is stationary, which means if you get a small p-value for this test, you reject the null and it indicates that the time series is non-stationary. Often your forecasting software for ARIMA modeling will do a unit root test like this and give you a p-value. So you have to know what's it telling you. Well, a unit root test like this KPSS unit root test, if the p-value is smaller than 0.05, then a test is saying there is the time series is non-stationary, so you better do some transformations. Now, some software, when you get a small p-value, it will automatically apply the correct transformations and then run the test again and show you, okay, before this test was significant, so I had a non-stationary time series, then I did these transformations, and now the p-value is above 0.05, so now I have stationarity, I'm no longer non-stationary. Okay, but you need to be able to understand the output of the software. So you need to know, okay, what does stationarity mean? What does non-stationarity mean? What is a unit root test? So now you know, unit root test is just saying whether this is stationary or not. Small p-value means the time series is non-stationary. Small meaning less than 0.05. Large p-values mean that you are happy, you're dandy, and you're fine, because you cannot reject the null that the time series is stationary, so you're going to conclude, oh, it's stationary. Okay. Practically, time series require 1 or 2 levels of differencing only to get rid of the trend. And so often software will run this test, find this non-stationarity, do differencing, do seasonal differencing if that's required, and then run the test again and show you, oh, we are no longer a significant KPSS test, so now we are fine, we have achieved stationarity. Whether you want to do seasonal differencing or not, so this test will, tell you about stationarity. Another way to check about seasonality, if there's seasonality or not, and if the stationarity can be caused by seasonality or not. So basically, do you need to do seasonal differencing or not, is what's called a seasonal strength factor, FS. And this is a number between 0 and 1, and that's the percentage of variance in your time series that's contributed by the seasonality. Okay. So if Fs is small, that means there's no stationarity in your time series. If Fs is large, that means there is seasonality. The textbook I am referring to you at the references for this lecture, that suggests 0.64 as a cutoff. So if your Fs, which is seasonal strength, is less than 0.64, then you're fine. You don't need to do seasonal differencing. But if it's 0.64 or more, then you should do seasonal differencing. I mean, if you're at 0.63, you might still do seasonal differencing. It's like on the boundary. But, anything less than 0.5, you're kind of clear. Anything around 0.6 or more, you kind of should do seasonal differencing. Okay, so now let's get to our actual modeling. So ARIMA models are a combination of models. First, we had autoregressive type of models, and these models have a very intuitive understanding. Past values of the time series can predict future values. So if you look at this equation, it just looks like a regression equation. You are predicting YT using the past values of the same variable, so past values of the time series. Okay, how many terms you need depends on how much autocorrelation you have and partial autocorrelation you have. The more the significant spikes in partial autocorrelation, the more the terms you'll need here. If the spikes are a few, you might only need 1, 2, 3 terms or 4 terms and something like that. And then there's obviously an error term. This is just basically a regression equation. Looks just like it, so you can intuitively think about it. You're going to regress the value of the time series at time t using on past values of the time series. You get a prediction model. Using that model, you can always predict the future based on the past values or the existing values that you have. So that's autoregressive model. Now, if you remember in the ETS models, okay, we had some state like the level, the trend, the seasonality estimates. If we use the state to predict, the forecast, make a forecast, then we compute the error here, which is a true value minus the predicted value. Okay, and then based on this error, we go and update the state. Okay, so the error is being used to update the state in ETS, which means the error carries important information. The error is that part of the time series which you were not able to guess correctly last time. So that's some important information for you to use for future. So MA models capture that that idea that past forecast errors represent a part of the signal that we missed, so we better use that to predict the future. So in the MA model, you just have a regression on the past values of the error. Error in the time period before the current one, error in 2 time periods before the current one, and so on. Okay, and so these are very intuitive ideas. Autoregressive model, the past values of the time series are going to predict the future. Moving average model, the past unpredictable part of the time series is going to predict the future. Because our model was not doing good on this part of the time series, so we try to build that into our model. Obviously, we don't have to choose AR or MA. We can combine both, and that's what an ARMA model is: AR plus MA model combined. Notice we're almost to a REMA. We got the 4 letters down. AR models, regression over past values. MA, pseudo regression. It's not just a basic regression like you're used to OLS regression, but it's kind of like a regression. And MA kind of like a pseudo regression, kind of like a regression on the past errors. So you can put them into one equation. So now you can do the like a bigger regression where you're using the past values of the time series, the AR part. You're also using the past errors, which is the MA part, and then this is the unpredictable part of the time series that you still, that you're not able to predict with this equation. Okay, so that's your ARMA model. ARMA, and now the ARMA model is basically an ARIMA model. The I refers to differencing. So if you had a non-stationary time series and you had to do differencing to get to stationary and then run the ARMA, because you can only run ARMA on stationary time series, right? So that will give you ARIMA. So let me just say that again. So this part, ARMA, let me actually clear this slide. Okay, this part, ARMA, this can only run on stationary time series. Okay, so what if we have like trend or seasonality? Then we need to do differencing, right? Well, especially trend. And we're going to handle seasonal ARIMA next. We're going to talk about seasonal ARIMA next. So ARIMA, just think about no seasonality for now, because we're going to do the seasonal ARIMA next. So think about ARIMA just for trend. And, autocorrelation is there, so you want to use ARIMA. So what you do, well, ARMA model can only work on stationary data. So I'm going to do differencing, which in this model is called integration for some reason. Whoever came up with this stuff, just call it integration. And so the I for integration means you're going to do differencing. And so that basically means you do the differencing. So you get y comma t, or y apostrophe t. That is just going to be your original time series subtracting a previous value. Okay. So ARIMA says you can't use ARMA on YT. So just calculate this, y apostrophe t, which is the difference time series, and run ARMA on the difference time series. So running ARMA on a difference time series is called ARIMA. That's it. ARIMA is easy peasy lemon squeezy. The AR part is using past values of the time series. The MA part is using past values of the error. And the I part means you will difference if required. If required, you're going to do differencing to take care of the non-stationarity. And that's ARIMA modeling right there. So when we write ARIMA models, okay, just like ETS model, remember ETS model had 3 parameters. We had ETS, the first was error, which could be additive or multiplicative, right? E for error, T. Then the second was trend. You could have no trend, or additive trend, or additive dampened trend. And the third was seasonality. You could have no seasonality, additive seasonality, or multiplicative seasonality. So you had 3 parameters to specify the exact ETS model. Similarly, for the exact ARIMA model, because there's millions of ARIMA models you could build, you have to specify 3 parameters, P, Q, and D. P tells you how many terms in the AR model. Do you have just 1 passed value of Y, or 2 passed values, or 3 passed values? So if P equals 2, you'll use this and this term only. If P equals 3, you have YT minus 3 as well. If P equals 4, you'll go to YT minus 4 and so on. Okay. D means the order of differencing. For all practical purposes, D is always going to be 1, and sometimes really D will be 2. You need 2 levels of differencing. So D is how much differencing you need to do, how much integration you need to do. And then the Q is the MA part of the model, which tells you how many past error terms to include. Okay, so if Q is 1, you just use epsilon T minus 1. If Q is 2, you use this one and this one. If Q is 3, you use 3 of them, and so on, right? So it just tells you how big your equation is. The bigger the P, the more the YT minus I, YT minus 1, YT minus 2, these terms are there. The bigger the Q, the more the past error terms are there. And the bigger the D, the more the integration, the differencing you do to make it stationary. So that's how you specify an ARIMA model in terms of its parameters. Okay. Now, in the past, how do we pick these? Now, the logical question is, well, how do I know what P, D, and Q to use? Who's going to tell me? Like, I have a timesheet, I have some data. Okay, how much past values of Y, like the P, what should be P? Should be 1, 2, 3, 4, 10, 12. What should be Q? What should be D? In the past, people used to, do unit root test, do a differencing, see if the unit root test is non-significant. Okay, you need D is 1. If you know differencing a second time, D is going to be 2. It's usually just 1 or 2. And for P and Q, they used to look at autocorrelation function and partial autocorrelation function plots, and they were rules of the thumb. Okay, if you see this pattern, it's gonna be an AR model, and then how many peaks are significant in a partial autocorrelation plot. That's gonna be the number of P. So there were all these rules of thumb that you could look at PSCF plot, ACF plot, and you could come up with, okay, I should try this P or this P. And then if you have, it was not deterministic. It'll not give you just one P. It'll say, okay, try this, try this. So maybe you're looking at the ACF plot and the PSCF plot. I say, okay, I'm going to have D equals and unit root tests, like the KPSS test. The unit root test tells me, okay, I need to do just one differencing, and then I get the test to be non-significant. So D is going to be 1. And then these 2 plots would tell me, okay, try P equals 2 or P equals 4. And maybe for Q, you want to try 1 or 2. And so you get 5 models here, okay? 2, 1, 1, 2, 1, 2, 4, 1, 1, 4, 1, 2, like that, like 4 models or something. And so then you try those 4 models and you compare them using AICC, and you pick the model with the best AICC. You do all this manually, a lot of work, run the model multiple times for each time series, right? All that's been automated now. So what we call auto ARIMA, like any software package worth its weight, and certainly you have libraries to do this in R and Python. And KNIME does it too. So all these free software does it, and obviously professional software, like paid software, also does it. Python or KNIME are also professional. There's a slip of my tongue. So all these free professional software, R, Python, KNIME will do it. Paid software will also do it. They will have something called auto ARIMA. Just give it the time series. It runs a bunch of models. It compares them on AICC, and it tells you this is the best model to use, and this is the forecast using the best model. So you don't have to manually examine, ACF, PSCF plots to determine P and Q. You don't have to manually do unit root tests. All of that's been automated for you. Click of a button, enter a Python command, does it for you. Okay, so your job has been made much easier, but it'll give you a bunch of output, and you have to understand the output. So you need to know what P is, what D is, what Q is, what differencing is, and so on. Okay. Okay, so let's look at an example. So this is Egyptian exports data. This is annual data, so there's no seasonality. Okay, so remember, annual data does not have seasonality. This is annual data, annual exports, right? Annual exports. Okay, so we don't have to use seasonal ARIMA. Seasonal ARIMA is sometimes called S ARIMA. We're going to talk about it next. It's not a big deal. Okay, you can easily do it. So if this was quarterly data, we did have seasonality, we do S ARIMA or seasonal ARIMA. But since we don't have seasonality, we'll just do regular ARIMA. Okay, some people just call seasonal ARIMA as well, because, you know, why not? You don't have to put an S in front of it. But so, like, you know, SAP, if you use SAP's ERP software, you know, its documentation will say S ARIMA for seasonal ARIMA, right? So some software use the term S ARIMA, some just call it ARIMA. Anyway, so we can just run ARIMA without the seasonal part because we have annual data, right? And when we run the auto ARIMA gives us this model, 201. What does it mean? P equals 2, so we'll use two values of past values of y, yt minus 1, yt minus 2. Differencing is 0, so we don't need to difference, okay? And then Q equals 1, so we'll use one past error. So look at our model equation, right? This is the estimated equation, so we have some constant, a coefficient for the past value of y, a negative coefficient for this, you know, past value of y. Remember, we're going to use two values, and then a negative coefficient for the past value of the error. So this, let me show you the different parts of the model. So this is your AR part of the model, and this is the MA part of the model. Okay, and this is your ARIMA model. The AICC value reported was 294.29, and ARIMA will give you a forecast. So this blue line, these are your point forecasts, right? These are all your point forecasts for the next few years where Egyptian exports you expect to go. And ARIMA very nicely gives us a prediction interval as well. Okay. And the prediction interval is very wide in this case. Why? Because you have so much variability in the data. You know, the ARIMA model is not doing you're not able to forecast very, very accurately, even though you built the best ARIMA model you could. You know, there's still a lot of variability, and this error has a lot of variance. There's unexplained variability in your data that's causing these big prediction intervals. You can't be really certain of your forecast. Okay. Now, if you try alternative models, so, you know, if you try ARIMA 400, for example, you get an AIC value slightly bigger than the value auto ARIMA gave you. So auto ARIMA value is optimal or very close to the optimal you can get. So it really gives you a great model to build your focus. And all this happens like by just clicking some buttons or writing a few commands in R or Python. So really easy that we have auto ARIMA. We don't have to manually do unit root tests. We don't have to manually look at autocorrelation plots or partial autocorrelation plots. All of that is taken care for us. Now let's look at seasonal ARIMA, okay? Seasonal ARIMA is very cool. It's regular ARIMA with the P, D, and Q, and then it has a separate component for the seasonal part. M is the number of time periods. So M is going to be 12 for monthly data, because you have 12 months in a year. So after 12 months, the seasonal pattern will repeat. M is going to be 4 for quarterly data. So it depends on what seasonality you're looking at, right? And then capital P, D, Q are for the seasonal component. It's kind of like, it's almost like you're doing two ARIMAs. You have the seasonal part of the time series. That's why knowing about time series decomposition is so important, right? Which is why I covered it in the beginning of the lecture. If you don't know time series decomposition, you'll be like, why am I have that separate PDQ for the seasonal part? Well, because just like ETS, which tracks seasonality separately, this ARIMA is going to handle seasonality with a separate model with this P and Q, and this is seasonal differentiation. This capital D is not ordinary differentiation. This is seasonal differentiation. Okay, seasonal differentiation. And the small q is just regular differentiation. That this regular differentiation will handle the trend, and the seasonal differentiation will handle the seasonality. Okay. And then you have the AR part to handle the seasonal signal, and the MA part with the bigger Q for the seasonal signal. So you call ARS, MAS. And then you have the P part to handle the non-seasonal, AR model to handle the non-seasonal part, which is trend and other stuff, and autocorrelations. And then you have the MA part to handle the non-seasonal part of your signal. So you have like 6 parameters, right? P, D, Q, small, and then capital P, capital D, capital Q. Okay. Auto ARIMA works perfectly well with seasonality. So it will estimate P, D, Q, and capital P, capital D, capital D, Q for you. So you don't have to manually select these values. I mean, you could try a bunch of values, try different models, see what works best. But Auto ARIMA will handle seasonality and pick it for you. Whatever software you use, Auto ARIMA might be called Auto S ARIMA. I don't like to call it SARIMA because it's basically an ARIMA model with seasonality, so I like to call it S ARIMA. But you might see software call it Auto S ARIMA instead of Auto ARIMA. That just has the seasonal part, the capital P, D, and Q. Yeah. This is an example of seasonal ARIMA, again using Auto ARIMA. So M is 12 because it's monthly data. M is 12 because it's monthly data, right? This is our data till here. So this is our data till here. And then in the blue here, that's our forecast. So the blue line, this blue line, that's our point forecast. And these shaded regions, that's your prediction interval. The forecast, your actual value could end up, is likely to end up somewhere in the prediction interval. Okay, so notice how nicely it captures the pattern. If you look at the seasonality pattern, like there's like this small leg here, you get the small leg in your forecast right here. Okay, so how nicely it captures the pattern, and the small p is 2. So, that's going to be the AR part of the regular model. One level of differencing, because you can see this trend, right? That trend requires differencing. One level of seasonal differencing, because you can see seasonality. So this will take care of the seasonality. This one will take care of the trend. And then for the seasonal part, you have an AR model with one previous value and an MA model with one previous error. Okay, so that is your auto seasonal ARIMA done. This is done with R because the examples I'm using are from the book, which is using R. It's in the references. Amazing book, but it could be done in any software. A lot of software these days support Auto ARIMA. Okay, now ARIMA and seasonal ARIMA are great at incorporating trend, seasonality, and past information. Notice they are different than ETS, okay, in some way. So ETS, the forecast is based on 3 things. State, okay, which has level, trend, and seasonality. That's what your forecast is based on, right? That's what you use to calculate Y hat. But this state also incorporates the past error, ET minus 1, because each time you calculate the error, you have the actual value minus the forecast, you calculate the error, you update the state. So state within itself in an ETS model captures the information from past errors. So the ETS model performs very admirably against ARIMA. ARIMA and ETS are very like neck and neck. They all, in many situations, they do an equally good job or almost equally good job. In ARIMA, capturing the error is more explicit. The MA part captures the error, AR part captures the past values, right? You don't have this state, you're like the separate state type of variables, okay? But you're still capturing the past values and the past errors, just like ETS does with the state. Okay, but what if you want to factor in more information than just the past values? and trend and seasonality and so on into your forecasting. A very interesting and practical use case is when you have price changing for a product over the year. So sometimes you run discounts, right? In holiday season, you run discounts. And so if the price is changing, the sales data, the historical sales data is being affected by the price that you set. Some months the price was low, so sales went high, not because it's a seasonal component or a trend, but because you were giving a discount that month. And next month the sales are low because people forward bought. They bought too much in the previous month because it was on sale, and now they're not buying this month, right? So temperature for goods like swimming clothes, party or picnic, goods to do with picnics, ice cream, these sales are often affected by temperature. So you may want to factor in historical price and temperature data, and you can still use this model to predict for the future because you know what price you're going to set next month or next week, right? You have a marketing plan, and you know what the temperature is likely to be next week or next month from the weather forecast, right? The average temperature. So you can use these variables in your forecasting because you know the advanced values of them to develop your actual forecast. So I want to run ARIMA, but I also want to include price data and temperature data into my forecast. So that is also doable. Now this is where ARIMA, why I prefer ARIMA over ETS. This reason is why I think ARIMA or SARIMA is more useful, not greater in some technical sense, but is more useful in practice than ETS models because I often have price data available. I often know my past sales, what was the price of that SKU or product. If you are doing category level forecasting, you have an average price for the category, like a weighted average price for the category, because sometimes the whole category goes on sale. So the weighted average price for the category will go up and down with the data. And you know what the price for the different SKUs will be in future, so you can calculate the weighted average price for the category in the future. And so you often have pricing data, you often have temperature data and other such variables. If you are selling large ticket items, think about appliances. Appliances sales are often affected by macroeconomic indicators like GDP, unemployment. If unemployment goes down, GDP is growing, people buy more appliances, people buy more homes, things like that, right? And so you might want to include GDP, and then you have the economists have predicted next quarter's GDP or next few months GDP, and so you can use that to build your forecast. So you want to add all these variables. ETS, there's no easy way, to add this additional information into ETS. There's no way. Okay. But you can incorporate this additional information into ARIMA or seasonal ARIMA. And when you do that, these additional explanatory variables are called X variables. You add an X next to it. So sometimes you'll see software which says we can do ARIMA X or seasonal ARIMA X. Okay. Or another term they use sometimes is called dynamic regression. Because remember, ARIMA kind of looks like a regression. And if you add additional variables, they call it dynamic regression. Okay. Because ARIMA is kind of like some sort of variation on regression. Just like in regression, you can add X1, right? B1, X1, B2, X2. You can add multiple X variables as predictors. Same thing with ARIMA models. You can add multiple predictors of the Y variable to that model, like price, like temperature, like GDP, like unemployment data, and all of that can be very useful for you. So with software, it's very easy to do. In addition to your time series, you just provide the time series for your predictor variables. You provide a time series of prices, provide a time series of temperature, and it incorporates that into the ARIMA modeling and does the forecasting for you. Now, let me show you an example. Here's the daily electricity demand in Victoria. Okay, and this the forecast here. This forecast here was generated using seasonal ARIMA X, and for X we passed it temperature, and because the use of electricity can be non-linear with temperature, so let's say the temperature goes above 85 or 90 Fahrenheit, people just turn on the ACs at full blast, and that just has a non-linear jump in electricity. We also pass it temperature squared. Just like in regular regression analysis, to handle non-linearities in data, you square the x variables sometimes. You can do the same thing with SNM x. You can pass it x and then x squared as a separate variable. So we pass it temperature, we pass it temperature square. It does the auto seasonal ARIMA with these x variables. And then for predicting the future, I believe the weather forecast here was showing that this is Australia, by the way, Victoria, Australia, was showing that we expect in the next few weeks the temperature to be average around 26 degrees Celsius, because remember Australia is in the southern hemisphere, so January is summer for them, right? The summer winter are reversed for Australia in the southern hemisphere, and so this is like a summer temperature. This is I guess this would be something like 60 or 70 Fahrenheit, right? So that's the expected temperature in the next average in the next few weeks. So we pass our model the expected temperature to use for the future values, and it gives us this prediction, gives us this point forecast, the blue line, and then the shaded blue regions are the prediction interval. So because, if the temperature we expect it to be higher, it should be a hot summer week, because summer is at this time in Australia. Let's say we expect the temperature to be like 30 degrees Celsius, then it might move our forecast up than what it gave us, right? So the forecast it does depends on what we expect the temperature to be, because in our seasonal ARIMA X model, we gave it temperature and temperature squared to generate the forecast. Okay. Now, whenever you use X variable, whenever you use ARIMA X or seasonal ARIMA X, you have to check with yourself, are you going to have values of this X variable for future? Because to build your forecast, the model is going to ask you, okay, what is the values of X for the future? Because it cannot, the forecasting equation has these X variables in it. So if you don't specify the value, you can never compute the forecasted value. So the examples I gave you, price, temperature, pricing, your marketing plan, the price for future. For temperature, you can get it from the weather forecast. For economic indicators, GDP, unemployment, you can take the economist predictions. But another shorthand trick exists where you never need to use the forecasted predicted value. And here's the trick. And many professional forecasters use this. Okay, let's say I have my Y time series. These are the values: 10, 15, 9, 17. These are the values. And this is my X value. This is maybe Y is like sales. And then X is like price. Okay. And I have pricing data. So at this week, the price was, $3. Then the price, I gave a discount, 2.5. Then the price increased to $3.25. And then I gave a deep discount for $2.9, let's say is here. Okay. So let's say I don't know the future price because maybe I'm doing forecasting and the marketing team has not finalized their sales plan. I tell them, hey, can you give me the future price after the forecast of my sales? They say, oh, we're just thinking about it. It'll take us another week to agree on the pricing. And so what do, right? You can't run the forecast. Well, this is what you do. You lag X by one time period. You calculate X t minus 1. So for the first time period, there's no previous value. So this is just blank. But for this time period, you use the value of 3. Okay. For this time period, so this 3 comes here. This 2.5 goes here. This 3.5 goes here. 3.25. Okay. And then what about the next time period? This is what we have to forecast. What's going to be the sales in the next time period? I don't know the price, but my lagged price, no, this is going to be the lagged price, xt minus 1, 2.9. So now I run my algorithm on this data where I'm not passing it in the price, I'm passing it in the lagged price. So if the price was low last month, I may see low sales this month because people bought a lot last month when the price was low. If the price was high last month, then I might see increased sales this month because people didn't buy last month because the price was high, they were waiting for a discount, right? So lagged price can affect your sale in the opposite way. So I base my model on the lagged price, which means for the next month, I know the price this month is the lagged price for next month. So this price moves here in this time period, and then I run my forecasting model, and this value here, the box, this predicted value is going to depend on the ARIMA X model. It's going to use 2.9 as the lagged price for this y hat value. And this is even more important when you're not using price. Let's say you're using variable like your competitor sales or sentiment from Twitter or social media sentiment index, something like that, right? Then, often you're in this problem where you want to use these X variables, but you don't know their future values, and so you can't use them with the ARIMA X. Just lag those variables because, often a lot of these variables, the value for any given time point has a correlation over time. So this value is correlated to this value. This value is correlated to that value. So if you lag the value, use the previous month's value as this month's value. That's what you're doing with lagging. You're still using some of the signal because this correlation over time. And so by lagging the variable, so what you do is you replace xt. That's what you do. You replace xt with lagged values, which are called xt minus 1. That's a lag of 1. If you need to forecast 2 time periods ahead, you need to use the second lag, you do xt minus 2. Okay, so just use a lagged value of the X variables to build your ARIMA X model, and then you won't have to wait for the forecasted value of the X variable to do your own forecast. Okay, let's talk about automated forecasting. Okay, why do you want to automated forecasting? Means you let the software or the algorithm just do forecasting for all of your products or all of your categories and so on without manual intervention. So every week or every day or every month when you get new data on sales, you can automatically rerun all your forecasts and update all your forecasts automatically. It's very nice. You don't have to do anything. The algorithm or the software does everything for you in a way. You may still have to break down the forecast from the category level to individual products. You may have, if the forecasting error grows too large, you may have to dive in and investigate what happened and maybe set some parameters around your automated forecasting. But it really helps you as a forecaster run forecasting for a whole bunch of SKUs. Now, often a forecaster or a supply chain planning division is dealing with hundreds or thousands or tens of thousands of products. I remember I talked to the supply chain planning team from Gordon Food Services. I believe they had a team of a few people, maybe 4 people or 8 people. It's definitely under 10 people or maybe 10, 12 people around that who were handling the forecasting for thousands of products, thousands of SKUs. How did they do that? They had this software which was doing automated forecasting, and they would just manage by exception. So for very profitable or key products, they would look at it, the forecast and do manual judgment-based adjustments. But for the majority of the SKUs, the forecasting was just automated, completely automated. Okay. So that's one reason, because if you were to start doing manually forecasting, 10,000 SKUs, you would not finish in time. Takes too long. Right? Unless you hire like a team of 100 people, and that's very expensive to have 100, supply chain master's program graduates or something like that, or statisticians, right? You have to pay them a lot of money. And the other reason why we want to do automated forecasting is forecasting need to be done by people untrained in time series analysis and unable to do programming, which is kind of sad. I think everybody should learn Python or R coding in this day and age. But, some people don't want to learn, or, they find it difficult, or for whatever reason, they don't have time. And so you may have purchasing managers or supply chain managers. They need to book order quantities with suppliers. They have no idea what the forecast is. And so what do? Well, if it's automated forecasting, just an automated report from the system, and then they can use that forecast in their decision making and do their jobs better. Okay. So what's the algorithm? If you want to use ETS method, the algorithm will apply relevant ETS methods to the data. It will select the best method using AICC or cross-validation, and then it will produce the forecast using the best method. Okay. Cross-validation is the idea that you save some of your data as a test data set. So if you have, let's say, 10 years of data, or let's say 5 years of data, you run your forecasting algorithm on 4 years of data, and then you test the same algorithm on the final year. The reason being is you don't want to overfit to the data. So cross-validation, what it does is you want to test the algorithm on unseen data that it was not trained on. And then whichever algorithm does the best on unseen data, that is the best algorithm to use for future. Okay. So it's a very popular term used in data science, used in machine learning, used in forecasting. It's very important to do cross-validation because otherwise, based on if you train on all of the data, you might see that your forecasting algorithm does really well. Why? Because its parameters were determined by this data. It's going to do well on this data. But does that mean it's going to do well on unseen data, future data? Maybe, maybe not. Right, so you always want to do cross-validation if possible. Anyway, either you use EICC or cross-validation to select the best method. The algorithm does it automatically for you, and this performs very well. This automated algorithm was tested on the M3 forecasting competition, where these forecasting competition, they give you like a bunch of time series, like 100 time series, and you develop, you come up with a forecasting method to forecast for them, and whichever algorithm does best, then they give like a ranking. Okay, this person's algorithm did the best, this came second, this came third, based on their performance on unseen data of those time series, of the same time series. Okay, so ETS by this automatic algorithm did really well. You do the same with AutoArima. Just apply AutoArima on all of your time series. The software will automatically use EICC or cross-validation to select the best AutoArima model, and then you can produce forecast and forecast intervals. Okay. Optionally, you can run both auto ETS, like this is like automated ETS, AutoArima, and then do cross-validation to pick whether Arima does better for you or ETS does better for you. Obviously, if you have other X variables like price, temperature, then you have to stick with Arima because ETS has no extension right now, which factors in additional explanatory variables. Okay. Note, AICC cannot be used to compare models from different model classes. You can't have an ETS model and look at its AICC value and compare that with the AICC value for an ARIMA model and say, oh, ETS has a smaller value, that's better. The AICC values can only be compared across the same class or category of models. So ETS models, you can compare them, rank them on AIC or AICC values. ARIMA models, you can, or seasonal ARIMA, ARIMA X models, you can rank them on AICC values, but you can't compare an ARIMA with an ETS model on AIC values. You can compare them using cross-validation because cross-validation will give you like a MAPE figure or MAD figure, mean absolute deviation, mean absolute percent error, and then you can rank them or compare them based on that, but you can't do it with AICC values across different model classes. Conclusion. ETS and ARIMA, including seasonal ARIMA and ARIMA X models, have been shown to have very good performance over a wide range of time series, very widely used in practice, in real life, in industry. They use these models. They're built into many ERP systems like SAP. They're built into many forecasting software. Free libraries available for R and Python if you know some coding or can learn some coding and do it yourself. Okay, and the book on the references slide, this first book by Hindman and Forecasting Principles and Practice, is a free, available online. This teaches you all the R code. It shows you the R code to do the forecasting in R. Forecasting using ETS and ARIMA can be automated. Free libraries are available. In practice, automated forecasting is expected to work really well or reasonably well at the product category or subcategory level. It will also work well for products where you have a lot of historical data. For products which are new products with no historical data, you will do it at the subcategory or product category level and then break up the category level forecast into the new SKUs based on judgment forecasting or some sort of ranking by salespeople and so on. Doing forecasting in real life often involves adjusting data for outliers and missing values because data is messy. You may have a strike, you may have a storm shut down some business, so you may have a lot of zeros in your data which are not really zeros, but the business was just closed, things like that. You may have some outliers you may have to clean, and sometimes the forecasting software, professional forecasting software, will help you interpolate, like a moving average interpolation, to interpolate and smooth over these values. Instead of a zero, 0, you put in the moving average value. Instead of an outlier, you put in the moving average value before you run the forecasting algorithms. So cleaning the data is often necessary in real life before you go and do the forecasting. And that is all. You have enough concepts and enough knowledge now to be able to use learn R and Python for forecasting, or use professional forecasting software, or use the forecasting tools built into SAP or other ERP software. You can read the documentation, you'll see this terminology, you'll understand the terminology, you'll be able to learn the software and do this on your own. So thank you for staying with me for this long presentation. These are some references you can go to. The ones in colors are very important. You can look at those to learn more about these topics.